Hello, everyone, and welcome to today's public webinar with TPC entitled VFDs, Variable Frequency Drives, and How They Work. My name is Ryan Smith, and I am joined by our TPC instructor, Marty Redmond, who's going to walk us through all the ins and outs of how VFDs work today in this public session. We can obviously only cover so much in 1 hour, but we're going to do our best to give you a little burst of information and a little public knowledge about VFDs. So today's session is live today. So I wanted to remind everyone before we jump into the meat of today's session. Today is being recorded. So this recording of this session will be made available on the TPC website within about 2 business days of today's session. And also, I wanted to let everyone know that on top of the recording, we'll also see the PDF of the slides available to you on the website, available for you to show and to look at as well. And finally, really today is live. So I really encourage everyone who is here to participate in the session by asking questions. So there is a Q&A button. That's where we really want you to focus your attention. The Q&A button where you can click and type in any question you want for Marty. And him and I will be able to work together and answer those questions. I'll pose the questions on your behalf to him as our host at the end of the session. And without further ado, I will hand it over to Marty and we'll start talking all about VFDs. Thank you so much for being here, Marty.
Thank you, Ryan. Thank you, everybody, for being with us this afternoon. We're going to touch on a few things with VFDs. We just have very little time, so we're going to go over some things that are kind of key points to them. Found basically that in my years of experience instructing at TPC, that people know very little about VFDs, and that's how we get into trouble. So we're going to kind of go through some of those things, and it's kind of knowing a few things and asking the right questions helps us go a long way. So with that, I guess we'll get going here. Well, why would we use a VFD? Well, there's lots of reasons. But it's a solid state controller. That means that there's very few moving parts in them. And with a VFD, we get rid of that main contactor that we typically use for a cross-line motor starting. So therefore, we get rid of a mechanical device that we know is going to fail someday. We get rid of those contacts, arcing and sparking, as we open and close it while it's running. And so those are good things to get rid of. We also get rid of the overload block, so we don't have those heaters that we would typically replace, or they burn up once in a while on us, and the contacts that are in the relay block fail occasionally. So there's quite a few things that that the VFD really helps us get rid of some old technology. Not that it's bad technology, but we have some things that are a lot better, and solid state control is one of them, and they've come a long way in the last 30, 40 years. So a lot of good things to do. So not necessarily bad, but solid state's a good thing to replace a lot of that old equipment. One of the other things we can do with our solid state VFD is that we can reduce voltage start, which means that we can ramp that drive up as fast as we want to or as slow as we want to, which then makes it easier on the drivetrain and all the equipment. I mean, if you think about usually when chains break, they usually break when you're starting up the equipment. If you have belts, when you start up the equipment, you hear a lot of squealing and all those kind of things, and that's wear and tear on pulleys and belts. So with a VFD, we can program it through its parameters to ramp up at whatever speed we want to. We can even skip certain frequencies if we want to. And therefore, I would tell you that a VFD can be probably one of the best maintenance tools you can buy. It's a great preventive maintenance tool in that it really reduces a lot of wear and tear on the drivetrain. It reduces a wear and tear on the couplings and all those kind of things that we typically just, when we go across the line, boy, we get that full power right away and things jerk. Well, we don't have to do that with a VFD. So by introducing the right parameters into the drive, we can really reduce that. We can start things up and have it go much easier. Well, we can also do that on the stopping side of this. So a lot of equipment, when we do across the line, when we turn it off, it just coasts down. Well, with a VFD, we can control that time at which it takes to go from full speed to stop. And we can ramp it down as quickly or as almost as long as we want. So there again, we're taking a lot of strain off of the drivetrain, depending on what's on the conveyor or whatever it is we're speeding up or slowing down, may increase the longevity of that equipment. So really good device to have for some of these things. Cost savings. Well, we mentioned that we're getting rid of a lot of moving parts, so that's a good thing. But cost savings really helps us with VFDs when we get into variable torque applications. A lot of you probably have fans and pumps, and they don't require full horsepower or full speed all the time, depending on the system. So if we program it, and it has to, the parameters have to be set for variable torque versus constant torque, we put it in variable torque, we can save some money. We don't have to put out 480 volts to the drive. We don't have to have it running full speed all the time. So we can save us a lot of money, because if I'm only putting out 300 volts to the drive, 20% of the time I'm saving some money. But just remember, the drive has got to be set, because most of them, are default to constant torque. So it has to be in your parameters, it has to set up. We'll talk more about that later. Motor protection. Well, with across the line motor starters, we have our overload block, our heaters we've had for years and years and years. And they work, but they don't work as well as the ones in a VFD. And I get to program that into my VFD. And the other thing I can do is a VFD can have torque limiting. So with typical motors, the motor has to go over amperage to create the heat on the heaters to get it to finally trip out. But with a VFD, if I want to, I can say, hey, when I reach a certain amount of torque, I'm just going to shut down. So I could be protecting my equipment or whatever I'm moving on that equipment. And I don't have to wait until it gets way overloaded to shut this unit down. I can do it on torque. So again, it's in the parameters, you have to set it, but it's another way to protect some of my equipment. I don't have to burn belts off and things. I can say, whoa, I'm drawing way too much current here, and I'm going to shut it down. So I don't have to wait for the overload. So we have a couple of different ways to protect our motor. Also, it will protect it with looking at the voltage from phase to phase and current phase to phase. So a lot of different ways we can do that across line motor starters can't. They can help your power factor if you have problems within your facility. I would just tell you that before putting in multiple VFDs in any place, a power factor study of your facility is probably a good thing to have, to know what the frequency in there looks like, what disturbances are in there, because VFDs can create some disturbances in your internal grid. And so it's kind of nice to know, when I first put it in, what did my frequencies look like? Were there disturbances or not? And so with a VFD, yeah, I can help my power factor. And everybody knows you want it up in the 80s or 90s. And when it gets below that, the utility usually charge you money because your power factor is too low. This is something that we is much better than across the line motor starters, is the communication. Motor starters, the old ones, we usually know when they trip out, and we know when we turn them on, and we get that information from auxiliary contacts. But with a solid state drive and a VFDs, we can communicate through the PLC 485 communication ports, and it is so much easier to program through that system. I don't have to go to the drive and work off a pad on the drive. I can do it right off a computer someplace. So communication with all of my equipment whether it's a PLC or all the other drives or whatever, they can all communicate and they all know what's going on. So when I get into a situation like a production line and a drive trips out, all the other drives know that drive tripped out. So we're talking very much faster than we typically would going through a PLC and then out, or just limit switches. So communications is much easier and faster. Almost all VFDs that I know of, when they trip out, whatever that may be, whatever may cause that, they have a set of parameters in there that keep track of the fault code. So did the drive trip out on high voltage? Did the drive trip out on low DC bus voltage? You know, was it just too much current? It's going to keep track of those. And depending on the drive that you have, may keep, you know, more of those fault codes in memory than others. But with the pad on the front of the drive, you can go right to where the fault codes are stored and you can see what it tripped out on. And obviously, if it's tripping out on the same fault code all the time, like maybe high bus voltage, then maybe we need to put some filters or isolation transformer or something in front of our drive, because something probably in your facility is creating a spike, and all of a sudden that is coming in and creating a high voltage. And, you know, one of the things that we know with solid state equipment is that they're designed to protect themselves. That's the goal. They're not going to let it draw too much current. They're not going to let it run on high voltage or low voltage like a cross-line motor starters will. It's going to turn itself off to protect itself. So that's another advantage to having the solid state and all these diagnostics in there, is that I can find out what happened. Where, you know, the cross-line motor starter, I'm going to have to do some checking. There's nothing that I can just push a button and say, hey, you know, the voltage is too high. So lots of good information there, but you have to use it. You have to go there and get that information instead of doing what most people do, which is take the disconnect and turn it off, turn it back on, start it back up, and then it takes off. And we never really found out why it went down. So we want to know those, because if we have a problem, we want to fix it and make it go away. The other advantage of VFDs is, yes, I can reverse the motor, but I don't have to have a reversing contactor to do it. So typically across line motor starters, I got 2 contactors. I got at least 1 set of overloads, maybe 2, depending on what kind of motor it is. And so I don't have any of that with a VFD drive. I can ramp it down, I can ramp it up. I can't go backwards until it's went down and stopped. And as soon as it stops, then it'll go the other direction. I can't stop it while it's still going. It will trip out. So there's a lot of good information here, and that I don't have all that mechanical stuff. So I get rid of that. So just another good reason to have one. A lot of the drives have parameters that you can go into and set so that you can go through a momentary power loss. Just because the voltage dips or the lights blink or something doesn't necessarily mean the drive has to shut down unless you want it to shut down. So it's getting back into your drive manual and finding out what I want. And then also you have to know about your system or the machine or whatever this drive is on. And, you know, if I lose voltage for a cycle or 2, do I want it to shut down, or is it okay if it keeps running? So these are all things that, you know, one of the parameters that you need to know what you need to do as part of setting up the drive. So back to knowing your equipment. A lot of the drives, the smaller drives, can go single phase to 3-phase. So in your home, I guess you could have, you know, put a VFD, I don't know, on your drill press or your bandsaw or something. And if you want to vary the speed instead of changing pulleys. So some do that, some don't. Again, you know, it depends on your needs and what you want to do. So there's just an awful lot of things that a VFD can do. And of course, varying the speed of the motor is one of them. And so with our drive, we can have many different things determine at what speed this motor is going to run. Maybe it's the flow of water in a pipe, you know, maybe it's a level of something in a tank. It can be airflow. It just can be all kinds of things that we can put a 4 to 20 milliamp or 0 to 10 volt or go through our 485 communication cable and speed this drive up or slow it down to whatever it is we want it to be. So there's just a lot of options, and back to understanding the system or whatever it's on to determine what options I want to use, how fast I want to speed it up, how fast I want it to slow down. All of these things are things that I need to be on my checklist of things to do. So this is just another good one. With all our webinars and presentations, we got to throw a little safety in because it's really important. With VFDs or cross-line motor starters or whatever, mechanical safety is always a consideration. We have lots of stored energy in different places, and we need to know what that is so that we can block it, chain it, or whatever, and it won't hurt us or come down or whatever. So that's back to knowing my machine. Electrical safety considerations, well, a lot of you are familiar with 70E, and 70E kind of tells us how to do things. OSHA says we're supposed to be safe, but 70 tells us how to do that. It's a best practice standard. And so we've got engineers and some very intelligent people out there trying to figure out how all this stuff works. And they've given us the best practices to do certain jobs at certain voltages. And we should use this book and use the PPE that they tell us to use so that all our workers are safe. Everybody's safe. So obviously, all of us have been shocked, and one time or two, I guess. And usually the only reason that most of us are still alive is because we weren't the best path for the current to flow. And that was a good thing. But you have to remember that, you know, whenever you're testing voltages and stuff, never be grounded. And standing on a concrete surface is considered grounded. So think about what you're leaning against. Think about what you're standing on. Do I need dielectric pads? Do I make sure the gloves I have on, you know, what is the voltage? I need to know 70 and follow your electrical safety program to make sure that I don't get shocked. I guess a good one is probably, you know, just turn the power off. That's a good one. Arc flashes and arc blasts are usually caused by humans. Arc flashes a lot of times happen because people are opening up disconnects while the load's still on. We're supposed to turn the load off first, then open up the disconnect. Get rid of the current as much as you can first. You know, shut down things in a normal manner. Don't just pull a disconnect switch unless it's an emergency. Somebody's getting hurt, maybe you have to go to pull it. Arc blast, typically, you know, we're dropping tools or putting screwdrivers in places and when we shouldn't be. And if you have a good safety program, I would tell you that there's usually procedures and whatnot to go through. So these things don't happen very often, and we don't want them to, but they do. And we have PPE to protect ourselves from these things. So make sure you're wearing it, guys. Safety, you just have to make a personal commitment to safety. If you're not being safe at home, you know, why not? I mean, don't be just safe at work. You got to be safe at home. You got to be safe all the time, guys. As I said, OSHA tells us to be safe, and 7E gives us the standard on how we can go about accomplishing that task. So whatever we're working on, it's important. It's important that we follow the 8 steps process for establishing and verifying an electrical safe work condition. So in 70E, it goes right down through the steps on how we're supposed to turn the power off, how we're supposed to put things in safe conditions. It's not every possible piece of equipment will fit into the 8 steps, but most of it does. So All we're trying to do is put that machine into a safe condition so nobody gets hurt. That's why the very first step is always turn the power off. Power's not on, it's very not likely to get shocked. And make sure that you verify all sources of power, because there's a lot of panels and a lot of facilities where there may be 3 or 4 sources of power coming to that panel that they are not labeled on the front of the box. And somebody turns that 480 off and thinks that it's dead in there, and it's not. That's why we're supposed to check things. So we talk about test equipment for VFDs. Want to make sure that we have the right meter, true RMS meter. The cheaper average sensing meters can be as high as 10 to 30 to 40% off in actual true reading. So we need to make sure that we have a true RMS meter to do that. And we need to make sure that we have a category rated meter for the location we're in. So if I'm in a building, I can use a Cat 3. If I'm outdoors, I have to have a Cat 4. So, make sure your meter's been calibrated, tested, whatever manufacturer says, OSHA says, if they say every year, then you should get it checked every year, recalibrated. But, make sure it's in good working condition. The leads and everything are good and don't have cuts and things in them. It's back to, safety first. Talking about our main components of most VFDs, they're almost all very similar. We have our 3-phase 480 volt input power, which most drives are operating at. And so the very first section of the drive is an AC to DC converter. So we have some diodes in there. Diodes, like a check valve for electricity, allows it to go one way and not the other. And everybody knows that alternating current goes both directions. So here we're going to stop that, and we're going to have a DC bus. And on our DC bus are capacitors. Depending on the size of the drive or whatever, depends on how many capacitors that are. But one thing you have to remember is that capacitors charge at peak voltage. So the voltage we typically read in our meter, 480 volts, is not peak voltage. That's our average voltage on 480 volts. Our peak voltage is going to be somewhere around 670 volts. And so that's what the capacitors are going to charge up to. And that's why your DC bus is going to have to be, when you check it, is going to be somewhere around 670 volts. If you got 480 volts on your DC bus, your motor is not going to run. So then we take our DC power and we invert it back to AC through some IGBTs. This is where we start changing the voltage and the current. We can, the frequency. By turning on and off these IGBTs, we can affect the voltage on it and the frequency. And that's what we're sending out to our motor. It looks pretty ragged as far as a cycle or a waveform if you have an oscilloscope, but it will look like a waveform, and it has to because we're on an AC motor. Now, some motors have what we call tach feedback into the controls to let us know how fast that motor is really going. So we told it to go some speed, and we're going to get some information back into our controls. Now, almost all drives do somewhat the same thing, but the controls and the pads and the parameters have different numbers and all look different, but it basically does the same thing. And this is one of the reasons why you're going to need your drive manual to help you get through and know where all the parameters are you need to look and what they all do. So we talked about, operator controls. I can control the drive with a stop start station just like I do a cross the line motor starter. No different. Or I can go back to that communication port 485 and control it through a drive system. So whatever network that is. Almost all of the VFDs will have a display on them. And most of them will display probably 6, 7, 8 different functions in the drive. So if I want to check incoming voltage, I can just push a button on the display and it'll take me and tell me what the voltage coming into the drive is. If I want to know what my DC bus, it'll tell me. If I want to check current, it will probably tell me. If I want to check the frequencies, there's several of them, and they'll all be in your drive manual and tell you what each one of the codes mean. And so, you know, there's a lot of information to be had there. You don't always have to get your meter out to check a lot of things on the drive. So it's important that you know what it's supposed to be, because if you don't know what it's supposed to be, then whatever it tells you, you know, how are we going to know that it's right or wrong? So keep your drive manuals handy. And one thing I would tell you is sometimes the parameters, settings, and numbers change with new versions of drives. So make sure that the manual you have is for the drive that you're working on. They may look the same, but internally they may have made some changes. So always need those drive manuals. They're very important to you. Things to think about when selecting a VFD. All I would tell you in my experience is a lot of different manufacturers of drives. They're all, almost all of them are very good, especially the main manufacturers, Siemens, Allen Bradley, Danfoss. There's just a lot of different ones out there. But if you don't know your equipment, if you don't have the right drive for it, you're going to have problems. I mean, it's an electronic device. We already know that it's going to turn itself off more than a cross-line motor starter ever did, just because it's not going to let itself get hurt. So it's going to turn off rather than let overcurrent or something go through it. So we're going to have some issues there. So what I would tell you is that it's all about the load. You need to know about the load. People typically say, well, you know, great, we're gonna put this drive on there, and they don't go out and check the current on the existing motor, what it's doing, what speeds it's running at. Talk to the operators, how often does it trip out, and those kind of things. Those are all really important pieces of information to know before I select a drive. So you got to do your homework. If you've got an existing motor that you're going to put a drive on, you better learn what's going on first. So back to all those loads and operating conditions. Am I turning it on and off very quickly? Does it run all day? You know, what are the loads? Does the load vary? Do I get shock loads? You know, what happens to this thing? I need to know all of those because they're going to cause current. And this drive is not going to allow too much current. It's going to shut off, and I don't want it shutting off. I want my system to run, my machine to run. So I need to go out there and put amp meters on it and check it for, I don't know, how many days you need to check it to make sure it's gone through all its different cycles that it goes through. Do I need feedback? I mean, I don't know what this motor is and how important the speed is, but it might be. If you're going to put it on something where you're metering something into a process, you better know how fast that drive's turning, because every turn is so many pounds or whatever of material going into the process. And I need to know what that is to make sure that my process comes out the way I want it to. So I would tell you that the very first thing I have to know is about my load. I have to know all the conditions that are happening out there. Talk to the operators, best friend you'll ever have. Buy a drive on current, not horsepower. There's a lot of manufacturers out there that are going to try to sell you a 20 horse drive. Well, what if my motor's doing 20 horsepower worth of work and I don't know, but somebody changed the overload so it doesn't trip out anymore? Well, that motor's going to do 22 horsepower worth of work until it gets too hot and burns up. It may someday, but it may not draw 22 horsepower all the time. Just maybe sometimes. Maybe somebody puts more material on a conveyor or something and the load goes up. So I need to know what the highest current that motor draws. Maybe I need a bigger motor to start with. I don't know, but I can tell you that in my experience in industrial facilities, that motors that are installed by maintenance people, 60% of them are not installed correctly. They don't go to the National Electrical Code Article 430 and learn what they need to know to install it properly. And probably of that 60%, 80% of them don't either have the right overloads or fuses or breakers in them to help protect them. So before you buy a 20 horsepower drive, because you got a 20 horsepower motor, you better find out what it's really doing. And a lot of times it's doing a lot more than 20 horsepower worth of work. And you're going to be sorry when you buy that 20 horsepower drive and put on that motor, because it's going to trip out all the time. So just do your homework. Do your homework. That's all I can tell you. If you don't, that really great thing you thought you were doing isn't going to be such a great thing. I would tell you that a lot of people put drives on general purpose motors, type B general purpose motors, because they're less expensive than an inverter duty motor. But inverter duty rated motors are special. They cost more, and they cost more for a reason. They have insulated bearings, so current can't go through the balls into the shaft to ground. They have much more insulation on the windings, much more sticks and tie down straps inside on the windings so that they can't vibrate. Remember, we said that when we take this drive and we send that frequency out to that motor, it's a choppy looking thing. It's not a nice little curve as we normally think of a 60 cycle waveform. And so it creates a lot of forces in there, and we need to make sure that that motor has the right amount of varnish and right amount of tie down so that the winding doesn't vibrate, because if one copper wire gets loose and starts to vibrate, before you know it's going to short out and your motor's going to burn up. So inverter duty rated motor is the best way to go. I'm not saying that some general purpose motors run a long time on a drive, and it all depends on frequency and load and all those kind of things. So if you don't want to have problems with an inverter duty rated motor, is probably the way to go. Here it talks about external cooling. One of the things we tend to do, and a lot of manufacturers will tell you that, hey, you know, if you buy this motor and we can speed it up or slow it down, you can get rid of a gearbox. Well, that may or may not be true depending on your load. So it's kind of back to knowing about that load again. And in some cases during a production run or something, you may slow that particular screw or pump or something way down low, where that 1800 RPM motor is only turning, 900 RPMs or maybe slower. If that motor is turning slower, then that means the fan on the back end of that motor is turning slower, which means it's not blowing as much air across that motor, and the motor is getting hot. So if you're going to have periods of time where that motor is going to be running quite slow, you might need an external cooling fan. Most manufacturers of motors have one. Just take the shroud off the fan. They got another one that bolts right up to it, and it's got another fan in it. And you're going to need another motor starter and contactor. And so whenever you turn on the drive, that fan's going to turn on, and that fan is going to blow like that motor's running 1800 RPMs all the time, keeping that motor cool regardless of the speed that it runs. Okay, so that's another one of those considerations you have to think of when you're going to put this drive on this motor. So there's lots of reasons, and they do great things, but we've got to set them up properly. How will the drive be controlled? So in a lot of simple operations, it's an operator who has a potentiometer, and he just turns it up or down and controls the speed of that motor to suit whatever he's doing. But in a lot of cases, some people have a much more sophisticated production, and that drive will be controlled by a conveyor or something ahead of it that's actually producing the part. So if it slows down, the whole line slows down. Then it speeds up, the whole line speeds up. maybe flow, water flow. There's just all kinds of things. Pressure can do it. So, what do you want it to do? I mean, a lot of HVAC units now, the fans are VFDs, and they're controlling those fans. So they speed them up very slowly to start up, and much more quieter, and they can control things better with a VFD. So, how are you going to do it? What is it that's going to drive it or control the speed of it so that where it is? Because you got to know if it's something beside the potentiometer right next to the stop start button, you better know what it is. Installing them is very important. Go to the manual. They usually tell you a lot of stuff. You can go to Article 430 in the NEC, but make sure that the wire that you put in is not just the normal wire you've been running for all your cross-line motor starters anymore, because the insulation is not rated high enough. You're going to have some very high spike voltages in that wire, and the insulation is only rated to hold back a certain voltage. And if it's higher than that, it's going to leak through and go to ground, and it's going to trip out the drive. So we need to make sure that you install the right wiring. Myself, I'm a cable guy. I like every motor to have its own individual cable, and they make VFD rated cable. And so you don't have those problems. When you start mixing wires in a conduit, you better know what you're doing, because if there's different wires going different speeds, they can crosstalk, and you aren't going to be able to control anything. So installation is key to a VFD as well, and where you run the wires. So look into, all I can say is, go to the drive manual and installation and Article 430 in the code to help you install it correctly so that you won't have problems that you created yourself. And as we talked, going back to the drive manual or Article 430 in the code will help you get a better installation, and you'll have less problems. And the system hopefully will run all the time for you. So make sure you get these key installations. Excuse me. Not all applications warrant using a drive. So it's back to doing your homework and trying to find out why do I want to control the speed with a VFD? What is that? So write down those reasons. Why are we speeding up? Why are we slowing it down? Is there another technology that do it that doesn't require a drive? Drives cost a lot of money. Maybe just a gearbox will do it on a regular motor. I don't know, but usually when you want to spend money, somebody wants to know why, and I got to have some reasons. So what is all the reasons we want to put in this new great technology to control this drive? Overhauling loads can be an issue. Not so much with cross-line motor starters, but when I put in a drive and I have a heavy load and I stop it, when it is told to stop, it doesn't stop right away. It coasts a little bit. When it coasts, it does what is called regen, and it regenerates voltage, and it goes into the back end of the drive, and it doesn't like that. So the drive will trip out. The drive will try to ramp it down, but if the load's too heavy, it won't. So if I'm going to slow this big load down, I better know how much I've got so that I can be ready for it. So I can put braking resistors in. There's a lot of options if you look in your manual for your drives. A lot of options of things that I can buy that help me with this load, that gets rid of heat, gets rid of some of that current, because if your drive gets hot, it's going to kick out. That's all there is to it. So I need to know if I have an overhauling load, and a lot of times just getting a bigger drive, it doesn't necessarily mean I have to change the motor, but just getting a drive that can handle more current will help me get around some of these problems. So If you've programmed it so that it slows things down gradually, and you can get away from that overhauling load, great. But if it's too much, then you need to probably get a bigger drive. Shock loads. A shock load is when, I don't know, maybe you got a conveyor or something that's running along, and all of a sudden, whatever raw material you use in the facility just gets dumped on it. Well, if you can only imagine how much the current goes up for a short amount of time when all that weight gets put onto that conveyor belt. So they call that a shock load. And the drive has got to be capable of handling that additional current, that high current, for just a little bit. Because if it's too much, the drive is going to trip out again. So I need to know if I have shock loads. Duty cycles, stopping and starting. A lot of times that happens in production modes or something. Things that get stopped and start, stopped and start. Remember that every time the motor starts up, I get an inrush of current that's going to heat the motor up. It gets turned off right away, then the fan stops running. So if I have frequent stops and starts, sometimes it's just as easy as having that additional cooling fan on the back end of that motor to keep the motor cool. And the drive turns on and off. If you're going to put a drive VFD in a cabinet, you're going to create heat. So how are you going to get rid of the heat in the cabinet? The cabinet's got to get rid of it, because the ambient temperature in the cabinet gets high, the drive will trip out because the electronics are going to try to protect itself. So, how are we going to do that? And the answer is not open the doors and let a whole bunch of dirt and dust in, because then I'm going to have other problems. So I need to know what that duty cycle is. Constant torque loads, where the torque is always the same, but I may change the speed. So I need to know about that. Conveyors and things like that are one of those deals. Constant horsepower, we have that. So demand is independent of speed. So I always need that horsepower, but I may be changing the speed. Milling machines, things like that, a tool room or something. So again, guys, it's always learning about your load. Variable torque, as we talked about, is the money-saving application. So a lot of pumps. And what I would tell you, especially when it comes to pumps, I said earlier that it's probably one of the great preventive maintenance tools you can buy for some cases, and this would be one of them. I don't have that jerk on that pump impeller anymore, or the bearings or the coupling. I can make that all go away with a VFD, gradually ramp that pump up or blower or whatever that is, and take a lot of wear and tear off belts or couplings or whatever that might be. So there's a lot of good things that drive can do for you. And in this case, this is where we can also save a lot of money. Payback in less than a year, probably, on installation and the drive and stuff. So know what those things need to be. And again, you have to set the parameters to variable torque instead of constant torque. It's going to be in one of the parameters in the drive. And if you don't set it, then you're not going to save the money. And a lot of people, get things installed by contractors, and the contractors, I don't know who tells them to set it up, but they don't set it up for variable torque. So you're not saving anything. You just got to drive on a pump that's not saving you any money at all. Might be saving you a little bit on maintenance. I don't know.
A quick update, Marty, we got a really good amount of questions coming in the Q&A line.
Okay.
If it works for you, we can maybe start answering them in about 5 minutes or so, if that works for you.
Works for me.
All right, great.
Here, concerns for VFD operation. Many people put multiple motors on one drive. Can I do that? Well, yes, I can, as long as I know or I understand that all those motors have to run the same speed. So when I turn it up, they're all going to go up. And when I turn it down, they're all going to go down. And the drive has to be capable of current for the total current of all the motors. So whether I'm putting 3 motors or 4 motors or 5, I have to know what the FLA on all those motors are. and I have to buy a drive big enough to handle that maximum current. And I would tell you that typically if you're going to run multiple motors off a drive, I would tell you that every one of them needs to have a contactor and a set of overloads on it, so that I don't have one motor tripping out my drive and shuts all of them off. It just shuts one of them off. So there's lots of different ways to install it, but installation is key there if you're going to do that. This is kind of one for fans and pumps and things. Will the load be spinning when I go to start it? That's a problem for some drives. If it doesn't have the parameters where I can put into the drive to say, hey, this is going to be turning when I turn it on. And so it knows that, and it will bring that drive to catch up to that speed and then take off with it. So it has to know that it's a parameter in the drive. It has to be set properly. Here it says, will my source be switched while the VFD is running? There are some places that do that. A lot of people put emergency contactors in front of some of their drives. So it just depends on the process or your system. But if it's going to be switched, you have to know it, because a lot of the drives fault out when you take the power away from it because you didn't turn the drive off first. You took the power away from it. So that's just like a loss of power. It doesn't know the difference from the utility shutting it down versus somebody turning off a contactor or something for it. Can we get around that? Sure we can, but we got to set the parameters so it knows. Is the load hard to start? Is it a massive load? If it is, we need to make sure that the drive can handle the current to get it started. Again, just a bigger drive can do a lot of things for us. And then how long do we want to take to ramp that up to full speed? So those are all things to think about. External disconnects required between motor and drive. The reason this can be a problem is that if you're going to put a disconnect next to the motor and you're going to have another one in the motor control center or wherever your drive's at, if the one out at the motor is turned off, the drive needs to know, or the system needs to know, we don't want to try to start that drive with that disconnect open, because if somebody closes it, it could cause a problem, a safety problem, as well as an electrical problem for us. So make sure that your disconnects are interlocked into your system so that it's not a problem. Cooling required for drive and or motor. So back to what I said, when you're going to put that drive in a cabinet, how are you going to cool it? How are we going to dissipate the heat? And same way with the motor, we said when it's going slow, we need to make sure we have an external cooling fan on there so that we can dissipate some of that heat because the fan's turning so slow. So just some things to think about. There's a ton of things to think about, guys. All I tell you is that, this is a short amount of time to give you a lot of information about drives, but obviously that's why we have a couple drive classes. Back to some visual mechanical inspection, of whatever it's on. And, it talks about alignment and grounding. Grounding conductors get very little preventive maintenance to them. Cleaning the unit, cleaning filters, cleaning the little muffin fans on the bottom of your drive. All of those things are going to get dirty. Even if you're in a clean room, they're going to get dust and dirt on them. And you need to make sure that, maybe twice a year, depending on your environment. I mean, you can PM your way out of any problem, but if a bunch of dirt, dust gets on the heat sinks of the drive, then it's not able to dissipate that heat. It'll overheat and shut down. So you have to do some maintenance and maintain it to get rid of that. Electrical tests, very important on the motor, on the drive. When you started it up, what was the voltage coming in? Was the voltage going out? So if you have that information, it's very important to get down in a technical book someplace. Maybe you got an engineering book or something that you can put this information, because when things go bad or we start tripping out, well, let's Do we have the voltage we had when we started? You know, what's the temperature? All those things are important to get through. The best troubleshooting tool you guys have is the drive manual. If you don't have the manual, it's going to be tough to know what parameters to look at. And so you should have your manuals where your drives are so that anybody can get to it. And having the right meter, that's important, and the right tools, those are all important. But if you don't have that drive manual, you have really handcuffed yourself. You got one hand behind your back. Most drives have these 6 conditions that we should know, we should have written down. It should be in our technical, our engineering book or something, so that I can find them very quickly. Power. What was the voltage when we installed the drive? I know we talk about 480 all the time, but in most plants never have 480. They may have 485, they may have 475. I'm not really sure, but we need to know what it was when we installed it. Because we're looking for a problem, and we need to know. The DC bus voltage, as we said, on most 480 volt drives, it's 670 volts. Well, there's a display that's going to tell you exactly what your DC bus voltage is. And if you don't have it up close to that number, that drive is not going to run. So like I said, if you check it and it's 480, that drive's not going to run. You need a new drive. So I need to know those things. I need to have an SOP, standard operating procedure, for checking motors. I make sure I know how to check it with an ohm meter. I know how to check it with a mega ohm meter, so that I know if I have problems with insulation, or I have problems in between phases and all that kind of thing. So what is your SOP for checking a motor? And just remember, a motor, most VFDs do not light a megger. Don't put a megger on the back end of that drive, or you'll ruin the drive. You're going to have to disconnect the wires, the motor wires, from the drive if you're going to check them at the drive. And don't use the ground on the drive. Use a different ground. Okay, so make sure you know what those are. Enabler permissives. Enabler permissive signal is something that says, okay, it's all right for this motor to run. So what is that? There's a lot of conditions on processes. Do I have water pressure? Do I have air pressure? Do I have hydraulic pressure? Do I have a dust system that needs to run? Whatever that may be, I'm going to put that in there to say, yep, it's running, and now I can run. So what is it that's going to tell it to start? It could be a push button, or it could be something on your production line that's actually going to tell it to start. I don't know where all that stuff is, because when it doesn't start, where am I going to look? And I need to know, because a lot of building automation systems tell drives to start. There are air fans and stuff in buildings. And, I should know, I'm on a building automation, what rack, where's it at, and what output on that rack tells my drive to go. I shouldn't have to wonder what it is, and I shouldn't have to take the time to look it up. I should know it. So this is more information that's in your book. And where does it get its information to run at what speed? Where is that? Again, that's something that you ought to know. This way, I can troubleshoot this drive much quicker if I don't have to look for this stuff. These are the 6 things that are really important to know. I should have it right there by the drive. I shouldn't have to go look it up. We talked about checking fault codes in your manual. It's going to tell you what set of parameters to go to and what the symbols in there mean. So it's going to give you a fault name, a fault description, and maybe a corrective action. But if it's always tripping out on the same thing, maybe we ought to fix that problem. Okay, so it's really important to do that.
And without further ado, here is our announcement at TPC, right? This is an awesome segue, Marty, into our new VFD simulation. that TPC is actually in development on right now and in the final stages of development. It actually should be available to the public for folks to interact with a full simulation on VFDs and troubleshooting them in the next 30 to 60 days from the date of this webinar. So thank you so much, Marty, for your presentation. I really appreciate you sharing your expertise with us. We have a really good amount of questions coming in the line. Obviously, we won't be able to get to all of them, but I'm going to try to get the highlights of some of them and see what you think. Ready, Marty?
Okay, we'll try to answer them.
Okay, I think another an interesting one I'm seeing is this individual was referring to them as VSDs, variable speed drives, and was wondering, is there a difference between VSD and VFD in the terms of what it is or how it operates?
No, I just think that's a terminology thing.
Yeah, good call. What are your thoughts on shielded control cables, and would you recommend using them for VFDs?
Most definitely. Any of the controls have to be shielded. They have to be at least 3 foot away from power wires. 480 volt wires, the conduit does. You got to be careful. Yeah, if those aren't shielded, you're going to have a real problem controlling that drive.
Excellent. And so just to let everyone know, who is asking some detailed questions, we see a bunch of you are curious here. We've captured your contact information for some of you who want some more information. Definitely take one of our 2-day classes, right? These are available online, just like you're seeing here. You might be connected with Marty again during your next VFD class and be able to take it either virtually or as a class offered at your facility. So definitely let us know. We have not only a basic VFD class, which we're hitting on some of that information now, but an advanced VFD instructor-led class that can really take you all the way through the more advanced programming and understanding and troubleshooting of these variable frequency drives. Let's see, how about this one? Have you heard of such a setup, Marty, about and maybe pros and cons of having single phase coming into the drive and then the drive delivering 3-phase on the output, like let's say in a residential shop?
Oh yeah, yes.
Okay, and is there pros and cons? Is that recommended?
Oh yeah, I think, like I said before, you might have a shop bandsaw. Let's say that's real easy. And most shop bandsaws have maybe 3 or 4 different size shivs on them so you can control the speed of the blade. If I put a drive on it, I can have either 120 or 240 single phase going into it. And of course, then I'm going to have to put a different motor on that bandsaw. I'm going to put a 3-phase 230 volt motor on it. And I can control that. I no longer have to change shivs or anything. I can just use the potentiometer on the pad on the drive and slow it way down when I'm cutting, let's say, metal or something, and speed it way up when I'm cutting wood.
Excellent. And Marty, if you don't mind showing them the info on our last slide, we got definitely a touch point for you to say, hey, give us a call if you want to keep learning. And I actually was able to figure out this poll. So I think our last activity together is relaunching the poll. And for you all to weigh in on this question based on what Marty was saying, how comfortable are you working on these VFDs? Very comfortable? Pretty uncomfortable? How comfortable did you feel hearing what Marty had to say about these and you applying that in the field right now? Feel like you need more training? Maybe not. And then I'll share that results with everyone here who's sticking around at the end. And then our second question to you, you can click your answer, is what do you find yourself typically doing in the field with variable frequency drives? Installing them, troubleshooting them with a multimeter, programming the parameters, performing preventive maintenance, or maybe none of the above. You just have them in your facility, but you're not actually doing those tasks yourself. All right, I think we got some good responses. I'll give you just a couple more moments to register them. We got them flowing in. And I think the responses have slowed down. So I'm going to go ahead and end the poll and share the results with everyone here. Thank you for being here. And really, you see a wide range of experience levels. And I think Marty gets a chuckle out of that because we find that in the classroom as well. People come to our classroom as complete newbies to variable frequency drives, all the way to people who have been working on them for 30 years and never realized some of the finer points to them. Most of you are right in the middle. It's kind of a whole curve. very uncomfortable, ranging to very uncomfortable working on these right now. And then all across the map, many of you are installing, 22% of you are installing, 39% of you are troubleshooting, 31% are programming. So really, people are doing all sorts of different things and interacting with the drives. And like Marty said, that manual for the drive can be your best friend in troubleshooting, and also just getting official training on how to work, how to understand, and how to troubleshoot variable frequency drives is the best bet for you moving forward. Consider classes, consider getting a simulation and doing some online training as well on this. And I think it's just always good to continue learning, like we see here. Always pursue the journey of learning, whether it's a VFDs, electrical, mechanical, motors, pumps, troubleshooting skills, using meters, understanding lockout, tagout, electrical safety, arc flash safety. There's a lot of ways to pursue it, and it all circles around just being safe and being efficient in your jobs. Thank you, Marty, for presenting today, and thank you all for being here. Have a great day.